In this video, we will try to understand how are different state variables of a gas related. But what is a state variable? If we have a gas in a particular state and we want to completely define the state, the factors we need to know to do so are called state variables. So, to fully define the state of a system, we need to know the total quantity of gas, its temperature, its pressure, and volume. So if we say that two systems are in the same state, then all these state variables should be the same for both the systems. Note here that in thermodynamics, we do not consider time as a state variable. We consider time in chemical kinetics. Now, we will talk about ideal gases and the ideal gas equation which relates these state variables. Gases are the simplest state of matter which occupy all the space available to them. They can be visualized as a collection of very small particles in a continuous random motion, and the average speed of this random motion is determined by the temperature. Ideal gases have no interparticle interaction, so each particle is independent of each other. It is also assumed that the size of the gas particles is very small. Hence, the total volume available for their movement is the same as the total volume of the container. Before we go into defining the state equation, that is, an equation which relates the different state variables of a system, we will learn a bit about the state variables. We know pressure physically means force per unit area. Gas in a closed container is in a state of continuous motion and hence keeps colliding with the walls of the container. Due to these collisions, the container walls feel pressure. We call this pressure as gas pressure. We say that the gas inside the container has a pressure of P, which is the same as the pressure experienced by the walls of the container. Now, let's take a setup where two gases under different pressures are separated by a movable wall. The one which contains higher pressure will push the movable wall and in the process compress the other gas and increasing its pressure too. At the same time, its own pressure will also decrease. In time, equilibrium will be achieved and both the gases will have the same pressure. Same phenomenon would have happened if there was no movable wall and the different regions had different pressures. The gas will have a tendency to move from high pressure to low pressure until there is a uniform pressure throughout the gas. Now, if we apply an external pressure at one point of this container, the gas at its vicinity would also keep the same additional pressure. And as this pressure increase will not remain localized, soon equilibrium will be established and the whole gas will experience an additional pressure equal to the extra pressure applied on a part of this container. This is the origin of the Pascal's law. Next is temperature. Temperature decides the direction of heat flow. Heat flows from a body at higher temperature to a body to lower temperature. In this process, the hotter body will lose its heat and the colder body will gain the heat energy, and soon equilibrium will be achieved when the temperatures of both the bodies become the same and no heat flows. Similar phenomenon happens if we mix two gases at different temperatures. The one with higher temperature will have a higher average speed of random motion and the one with lower temperature will have lower average speed of random motion. And when they are together, they both will collide with each other and in the process exchange energy till the whole system attains a uniform temperature.
Now that we know something about these state variables, we will see how they are related. Let's see how is volume and pressure related. If we increase pressure on a gas, keeping its temperature and number of moles constant, its volume decreases such that pressure into volume remains constant. So P1 into V1 will be equal to P2 into V2. This graph depicts the same phenomena which is called Boyle's law. On this curve, pressure into volume remains constant at each point and hence this is also called isotherm. We can draw another isotherm for lower temperature and on this curve the product of pressure and volume will be lower and proportional to the temperature of this isotherm. Next, we will relate temperature and pressure. When we increase temperature, keeping other variable constant, the average velocity of the particle increases and they apply greater pressure on the container walls. The ratio of temperature and pressure remains constant given the other variables are unchanged. This phenomena can be depicted using this graph. This is called Gay-Lussac's law. On this line, the slope, that is pressure by temperature, remains constant. We can draw a similar curve for lower volume too. Next, we will relate temperature and volume. On increasing temperature, keeping other variables constant, the volume of gas increases proportionally. You can imagine this as two-step process. On increasing temperature, pressure increases. And to release gain in pressure, as we have assumed final pressure is unchanged, the volume should increase. We observe the same phenomena of thermal expansion in solids and liquids too. This change occurs in gases such that the ratio of temperature and volume remains same. This can be depicted using this graph. This is called Charles' law. On this curve, volume versus temperature, that is slope of this line, remains constant. We can draw another curve depicting same phenomena for lower pressure too. An interesting observation that can be drawn from this curve is that at very low temperature, the volume of gas reaches 0. This temperature is considered to be 0 Kelvin. Last is relation between amount of substance, that is number of moles, and volume. On increasing the amount of gas, its volume too increases, such that the ratio of moles and volume remains constant. Hence, N1 by V1 is same as N2 by V2. On combining these four empirical relationships, we get the ideal gas equation. Look at this and try to remember this as soon as possible. We would be using it a lot. Sometimes we might need to use a variation of this equation, like this one. Try to prove this equation from the original gas equation.